In this section, we're going to start looking at the process of optimization. So optimization means finding the global extrema on an interval. And we're going to look at both the cases of a closed interval, which is going to be our easier problem, and an open interval, which is going to require more work, noting that negative infinity to infinity, all real numbers, would be an open interval question. So to begin thinking about this, we need to think about the extreme value theorem. This theorem states that if f is continuous on the interval a to b, and this interval is important, this interval is what we call closed. Closed means that it has these square brackets, and bounded, which means that there is no infinity involved. So as long as we have an interval that looks like that, then we are guaranteed that f has a global minimum and a global maximum on that interval. So before we talk about why this is important, let's just talk about why this is true. All right, and we can kind of say the same thing we did with the mean value theorem. Start with any 2 points, A and B. All right, we have f of A and f of B, and then draw a continuous function connecting those points. And any continuous function that you draw is going to have a global minimum and a global maximum. Here would be the global minimum. And in this example, the endpoint would be the global max. And that's why it's important that we have a closed interval, because if this were an open interval, then the global max wouldn't exist because there would always be a bigger value. So let's look at, for example, x squared on the interval -1 to 1. X squared on -1 to 1 looks like this with 2 open dots. This has a global min, but does not have a global max. If we think about what's the biggest function value, it's going to be something close to 1, and we can get as close to 1 as we want, which means that there's no biggest value. So open intervals make this problem more difficult. Closed intervals guarantee there's going to be a global min and global max if it's a continuous function. Note that if we're allowed to go to infinity, then weird things happen as well. We can just blow up to infinity and there's no global max or min maybe. So now the question of why is this important? Why is it important that if we have this case, then there does exist a global min and global max? Well, this is called an existence theorem. It gives the existence of something happening. And when you're first seeing these theorems, they may seem like very simple theorems that aren't really telling us much. But in fact, they're very important because our goal is going to be trying to find the global max and the global min of a function. It's important to know that they exist before we start to try to find them. And they don't always exist. So an analogy of that is if I told everybody that there's $1 billion buried somewhere in the URI quad, nobody would drive to URI or go to URI or get out of their dorm and start digging for that $1 billion because you have no guarantee that it exists and you don't believe me that it exists. But if in some way I could guarantee that that was there, that the existence was now taken off the table, it is there, people might act differently, and there's actually it might be worthwhile to go search for that buried treasure. So we're going to use this theorem to help us when we have a closed and bounded interval. And when we have this process is going to be fairly straightforward. And here's how it's going to go. We're going to start with finding the critical points of the function because we know that the local extrema, global extrema have to occur at critical points. And note that because we have a closed and bounded domain, that the endpoints are always going to be critical points because the derivative does not exist at endpoints. Step two, once we have those critical points, we know that the global extrema exists, and we know it has to occur at one of those points. So we're just going to compare the function values at those critical points. We're going to plug in the critical points into the function. And note that we're going to find that when the largest function value we find has to be the global max, and the smallest one we find has to be the global min. I want to make very clear that without that closed and bounded domain, this process becomes much less straightforward and becomes more difficult. We are going to deal with both kinds of problems in this section and in the next section as well when we do application problems with optimization. So let's do an example. Find the global max and the global min of a function x to the fourth minus 6x squared on -1 to 3. Note that we have our closed and bounded domain. It looks like bracket A to bracket B, and we have a continuous function. And we need both of those things to use the extreme value theorem. So step one, we are going to find the critical points. And we find the critical points by finding the derivative of the function, which is 4x cubed minus 12x, and setting that function equal to 0. To solve for this equation, we're going to factor out a 4x. We'll be left with 4x times x squared minus 3, which means that we're going to have x equals 0 and positive negative root 3 as critical points. To find the square root of 3, you set x squared minus 3 equal to 0 and solve for x, and we get positive negative square root of 3. Note that we also need to find when the derivative does not exist. And in this case, there is something. It's always going to be at these two endpoints. Everywhere else, it's good to go. There's no weird thing happening with that derivative. So these are our critical points, and note that they all aren't going to be part of this because the negative square root of 3 is not in the domain. So our critical points are -1, 0, root 3, 3. So what we're going to do once we have those critical points is we are going to compare the function values at that point. So we're going to have f of -1, f of 0, f of square root of 3, and f of 3. Or we're plugging it into the original function. So we have -1 to the fourth minus 6 times -1 squared is going to be 1 minus 6. That's going to be -5. F of 0 is going to be 0. F of square root of 3 is going to be square root of 3 to the fourth minus 6 root 3 squared. That's going to give us a -9. And for 3, we have 3 to the fourth minus 6, 3 squared is going to give us a 27. So what this means is that we have the global max and global min has to occur at one of these 4 points. The global max is the biggest function value that we have. The global min is the smallest. So we're just going to say that the biggest one is where we have our global max. Note we could say this is a global max of 27 at x equals 3. But it seems that's kind of given when we find f of 3. And our global min is going to be at the square root of 3. It is the smallest function value we have. If we look at the graph of this below, we can see the global min and global max given at square root of 3 and 3. We kind of like cut this function at -1 to 3. If we look at on all real numbers, this wouldn't have a global max, and we kind of talked about that in the last video. All right, so if we have a closed and bounded domain, that's all we have to do for these problems, and that's good. And we want closed and bounded domain if possible. However, that's not going to be all the problems we deal with. So if we don't have that, there are more steps we have to think of. I'm going to write down these steps, or we've written down these steps here, but I want to make it clear that it does change per problem, and some problems are much easier to deal with, and some are going to be needing kind of all of these steps. The process starts the same way. We need to find the critical points of f because we know that global max and global min are going to occur at those points. Then we are going to test whether the critical points are local maxes or local mins using the first derivative or second derivative test. Then we're going to find the value of the local extrema in the function, or we could do that to see if it's going to be the biggest local max or the smallest local min. And then we're going to identify the behaviors of the function or any behavior near discontinuities. That is, we need to check if we are going up to positive infinity, or if we are going down to negative infinity with end behavior. That would mean that we don't have global mins and global maxes, and we have to check for those now. Then we're going to compare all the values, and we're going to try to make a decision on what's the global max if it exists. So here's the downside. These are some step-by-step processes, but it's not a great step-by-step process, and I don't think that you should be married to that, these steps. It really is going to change per problem. Some problems are going to be much easier than others, and it's going to be kind of just per problem. The best way to go about it is to have a good idea about the general shape of the graph. You don't need to know every single detail. You don't need to know concavity necessarily, but you need to kind of have an idea of, is it going down to infinity? Is it going up to positive infinity? Is there a horizontal asymptote? Kind of what's going on with those functions. And we'll get some practice so we can kind of see how we can go about showing what the global max and global min are. So let's start with an example. Same problem, but no domain is explicitly stated. So that means that it's going to be negative infinity to infinity, which means we have some more work to do. Note that we found critical points before of 0 and positive negative root 3. And we know that the derivative doesn't exist. There's nowhere the derivative doesn't exist, so there's no issue there. So these are our critical points. All right, we did that before. We'd have to find the derivative to find those points. So now just plugging those points in is not going to be enough information because we're going to have actually that no global max exists. But it might be worthwhile to to test whether these are mins or maxes. So let's do the first derivative test. And let's plug in 0, negative 3, square root of 3, and positive square root of 3. And by plugging in those, I mean plugging in points around those to see what the sign of the first derivative is going to be. So maybe we'll plug in -2, -1, 1, and 2 into the derivative, which is 4x cubed minus 12x, which we can write as 4x times x squared minus 3. So when we do that, we're going to get that this function is decreasing, and then it's going to change to increasing, change to decreasing, and back to increasing. And that's by plugging in -2, -1, 1, and 2 into the derivative, and we've done that before in the previous video. So what this means is that we have local mins at positive negative root 3 and local maxes, or local max, I should say, not maxes, max at 0. And that gives us some information about what's kind of going on with this um, function. In fact, we could probably graph the function at this point. We know that it's going to look something like this. All right, it might help to find what are the actual function values at these points. F of 0 is 0. F of square root of 3 is going to be negative 9. F of negative square root of 3 is also going to be negative 9. So if we adjust those points, we know we have a global min at positive negative square root of 3. Finally, it might be worth thinking about the limits. And this is probably too much work for this problem just because it's a polynomial, but we know that it's going to go off to infinity on the right and infinity on the left. It's going to look like this. So when you kind of put it all together, we know that there is going to be no global max because the limit as x goes to infinity of the function is infinite. So it's going to keep on going up and up and up on both sides. And there is a global min of negative 9, and that occurs at both positive negative square root of 3. So in this specific problem, I think that you could get away with less work. I don't think you necessarily need the limits. It depends on what you know, if you know whether that function looks like that shape or not. If you know it's going to keep on going off in both directions because we have a polynomial. And the more you know about these functions, the more steps you can kind of skip. You don't need to be so specific about everything. However, something needs to be said. You can't just plug in the function values. You need something more for these. Look at some more practice problems dealing with this in the next video. Before we do that, let's take a look at the function here. You have a graph of it. And we can see our global mins there. There's no global max. Because we're going off to infinity in both directions. All right, now I'll say, we'll look at some more practice problems in the next video.